everyone. Thank you for having me. We continue about neutrinos, another data release, a different one. This is not alerts. This is not these very special high energy events, but this is all track-like events IceCube has been collecting. This is about this new data release of 14 years of IceCube data that we plan to release by the end of this year or early next year. And the plan, and while this is obviously true that we will release this, it's not, it depends on your feedback, on the users' feedback, whether we manage to turn this release also into something that is usable for people outside of the collaboration. So I'm going to present about the data release and about the plans to release tools for analyzing them. You heard about tracks. I'm not going to spend more time on this. You heard about this from Marcos and now from Angela. The concept is the same. This is a data release of candidate mu and neutrino-induced events. This is because we want to have this very nice long signature that allows us to have a very good angular resolution on the parent neutrino direction. The resolution for the sample I'm going to be talking about is below 1 degree at energies above 1 TeV, and it drops below 0.5 degrees above 10 TeV, with an angular error floor that is about 0.2 degrees. Of course, the downside, as was mentioned already yesterday, is that with tracks, you have a little bit of a you don't have such a high resolution on the energy of the event, the neutrino energy, because tracks do not only travel through the detector, they travel also outside of it, depositing their energy also where you don't have your instrument detecting the light they produce. In any case, you don't get those images as a data release, you get something that is machine readable, you get numbers, and the experimental data are going to be released in as was done before, in a table that contains the arrival time of the event, the reconstructed direction in terms of right ascension and declination, the angular uncertainty on the reconstructed declination, and the reconstructed energy. For this data release, we cover the full sky. So you have northern events and southern events, and we have reconstructed energies that, depending on the season you look at, go from 10, 100 GeV up to PeV. This is the data release that was out in 2021. It included 10 years of IceCube observations. You see it had also incomplete detector configurations. Here IC stands for IceCube and 40 stands for the number of strings that were deployed at the time. So you had 3 years of incomplete configuration and 7 years of full IceCube detector. What we are adding now is 4 more years of full detector configurations, which will make the release go up to over 1.5 million events. We are also releasing updated calibrated events. So we are using the most recent knowledge we have of our detector and apply that to the most recent years, so complete detector configuration and IC79. And we have uniform processing for all 86 strings configuration data, which was not the case before. You don't only get experimental data, you also get some instrument response functions to use this data. First of all, you get the effective areas, one for each data set. These being the effective areas are for neutrino detection. So why are they useful? If you have a neutrino flux model and you want to know how many events you should expect in IceCube, you basically use this, convolve your flux with this function here, and you can get a number of expected neutrino events detected. This is an image coming from the previous data release. So this was the binned effective areas of the IC86 data sets for the previous release. Now we are updating it by cleaning them a little bit. So you can see that for the southern sky, here you have the neutrino declination and the neutrino energy. In the southern sky at low energy, we had a contamination of events that survive our cuts because they're misreconstructed as northern events where we don't have a low energy cut. And this can be super annoying when you want to build, for example, a PDF for your neutrino flux model, and then you happen to have non-zero contributions for this part of the sky. So we decided to clean this to make your PDF smoother. The other improvement is to the other instrument response function, which is called a smearing matrix. It's called a smearing matrix because it gives you the smearing from a neutrino event to the reconstructed observables you have in the data, basically. In IceCube, we have pair event simulations, Monte Carlo simulations, that I simply plotted on a 2D histogram, very finely binned here. You see we have some structures. I don't know how much you see it, but higher energy events are seen at the horizon, for example. We have absorption of high energy events in the northern sky, these sort of things. This matrix maps the true, gives you a probability, given a true simulated neutrino, it gives you the probability of the reconstructed observables in terms of muon energy, angular separation between the neutrino and the muon, and the uncertainty on the reconstructed direction. In the previous release, this matrix looked like this. It had 3 bins in sign declination for the neutrino. You can see you don't really capture all the features that you have in the real distribution. When you this was causing some problems. So if you try to reproduce some internal ice cube results, this would make it not so easy, because yeah, most of the sources we observe significantly are close to the horizon, and here you have only 1 bin that goes into even the southern sky with the processing of ice cube actually changes. In the new release, we're going to have smearing matrices that look like this. So the binning is much finer and the finest around the horizon, so where you have changes in processing. This should reflect much better what you have in real data. And by the way, this binning is also what IceCube uses internally for some analysis to build some of its energy PDFs. All right, so this is what you get with the data release. And additionally, we plan to release software tool that should help people to do some basics IceCube-like analysis with this data. This is SkyLLH. It was already released. So it's an open source Python software that was thought at the beginning by its first developers, Martin Wolf and Thomas Kontrimas, as just a very general tool to build likelihood, log likelihood functions and perform likelihood ratio tests. Then, of course, it's an IceCube tool, so it includes now many IceCube specific features. And for the points, for the data release, which is optimized for looking for point-like neutrino emission, it allows you basically to search for what IceCube usually searches for. So continuous and transient neutrino emission. So you can look for neutrino emission integrating over the whole 14 years of data, or you can look for neutrino flares, and you can also feed arbitrary energy spectra. This is, I'm gonna be careful with this because for the single power law, it always works. People have been fitting, as you can see for this example here, whatever they thought would be the emission for a blazar, for example. They've been fitting this with SkyLLH and producing limits that are energy dependent. But for example, then for a broken power, for a cutoff power law, I'm reviewing a PR right now because that breaks. So I'm gonna be careful with this, but in principle, you can feed your own energy spectrum. Here I have another example, which is from me. I published a paper where I needed to produce a Skymap, time-integrated Skymap, and I could do that with SkyLLH. SkyLLH was first released with a public data interface in 2023 by me, Martina Karl, who implemented the time-dependent, also the flaring search, and Martin Wolf, the original developer. And now in 2025, we plan to release an updated version that includes several improvements together with the new data release. In terms of performance, these improvements to the instrument response functions also then show to make us able to reproduce more closely internal IceCube results. These are 2 typical figure of merits in IceCube. So you see a flux as a function of the location in the sky. This is the flux that corresponds to the 90% confidence level upper limit you would set on the flux if you don't have any observation. So if you observe a null result, that's what you set as an upper limit for 2 different spectral indices, so a hard one and a soft one. And then you have the 5 sigma discovery potential. This is the average flux you need for a 5 sigma detection local, on average. What you can see is that here we tried to use both the instrument response function format of the previous data release and the new one. And the new one that is in blue is reproducing really closely the internal IceCube sensitivity and discovery potential, especially for soft spectra, which now are super interesting because sources seem to be soft for whatever reason, many of them. So this can be reproduced better now. And the other thing you obviously want to check is whether you can fit signals that IceCube has been fitting. So for example, NGC 1068, which is neutrino source with a very soft spectrum that IceCube identified in 2022. This can be done. So you can see this is the likelihood profile for This is a proxy for the neutrino flux. It's the number of signal events in the detector. This is the spectral index, assuming a single unbroken power law. So your likelihood is a function of these two parameters. You can plot the profile likelihood for the best fit values, and you see they overlap very well between IceCube result and data release results. And here I have a bunch of other sources. If you have your favorite one, there is another one, maybe it's one of these. They can all more or less be reproduced within some uncertainty. And then there is the second source, which is, we've just heard about it from Angela quite a lot, is Texas 0506 plus 056, detected in 2018, not only with the alert, but also with an archival flare. So after identifying the high energy neutrino, IceCube looked into its data and found another neutrino flare in previous data. And if we use the best fit time box published by IceCube, we can reproduce the flux parameters basically identically to the what IceCube has been publishing. And we can even search for the flare ourselves, but using, instead of the standard method, which was very slow, using a much faster unsupervised learning method that takes, it's 10 to the 4 times faster than what IceCube has been used so far, and identifies the flare more or less at the same location, although it finds a shorter flare. This was work done by these people here. I would recommend checking the paper. All right, and then my last two slides, the second to last, is about why did I think of asking Fabian to bring this work here. This is not real-time data. This is something we release and it's gonna be there, and it's not gonna change, but this can complement real-time studies. And the first example you can think of is actually TXS. After the identification of a multi-messenger event like that one, people looked in archival data and found another flare. And this made the case for that being a neutrino source much stronger. In IceCube, we do this kind of stuff. There are a couple of papers where a colleague looked for all alerts if there was a previous flare in the data. And another work which summarizes what we call the fast response analysis, which is looking for flares from alert events in the archival data, basically. But this is not something that is being done automatically. It's not something that outside people can do for whatever time window they're interested about, or just looking through the entire data set. So in principle, this is something that could be done, I think. Could be, we were thinking about ideas yesterday, so maybe this could be an idea for a project to extend IceCube, the IceCube contribution to the Astro-COLIBRI project. And this is my summary. So I showed you 14 years of IceCube data that are gonna be available to you soon, I hope end of this year, beginning of next year maximum. Together with the data, there's gonna be a paper that explains everything and more that I've been telling you, and there's gonna be a new version of SkyLLH, which is in any case on GitHub and open source. In general, I made this plot. It's not like something you should take too seriously because I've been manually selecting stuff. But the idea is that if you look at, having data available helps. People use that and publish paper and make science out of it. But if you add also a tool to use it, people use it even more. And this is something you've been saying yesterday as well. And we've been seeing this with SkyLLH as well. So I think this is super important work in general to make data usable for people. And yeah, that's it. Thank you.